All right. If you don't mind, if you would close the windows, I think that helps all of us with the audio a bit. Okay, so hopefully this all works. A tiny bit of sound here. So, okay. Um, Alrighty. This is session 3. I'm glad that everyone's, well, all of you are here early in the morning. And this is me for the first time. We're going to look into LSTMs and transformers. Let's have a quick look at what I have for us. We'll start out with a little recap of, and I'll have the meeting controls in a moment. That's great. We'll start out with a bit of a recap of what we've seen so far. We'll look at backpropagation, especially if we do this along a time dimension. We'll think about some problems with architectures like RNNs that we've seen before. And then really we have a pretty action-packed agenda for today. And there's a running betting pool going, I think, strongly stacked against me among the TAs and lecturers here. So everyone believes that we can't possibly do this in one class. We'll challenge them, and I think you guys can do this. So hold on for dear life. It's going to be a fun ride. We'll look at LSTMs, which are an interesting alternative way of doing things relative to what you've learned about recurrent neural networks. We'll do these in 2 directions. We'll look at attention, right? So an explicit way of saying where should the model look when making predictions, when making translations. We'll look at a particularly interesting flavor of attention called self-attention, which gives us like foundation for transformer models that are so powerful nowadays. And then finally, we'll look into transformers themselves, right? So the architecture that pretty much governs the state of the art of a lot of these problems at the moment. To hide this again. Let's see how long that sticks. All right. A quick recap. And when I say recap here, really the honest truth is this is a recap of things you've never heard before, right? So this is some things that may have been mentioned in passing sort of the last 2 weeks. So either in this very quick intro session or last week in Michael's first content session. Fantastic. So this we're going to do slightly differently next time. This is now probably not screen. All right, more of this. So we'll try to recap those, and there may be concepts that are out in the world and you've seen them in the wild. I just want to make sure that we're all somewhat on the same page with some of these concepts, and then we'll dive in and do interesting stuff with them. Okay. We've talked about embeddings, and this was me in the first session talking a bit about you are having these embeddings, right? And really, what are they? They're distributed so-called representations. So it's a dense vector in which we don't have this property anymore that each dimension is one word, right? So dog and cat, eat them or do other things with them. But instead, here the idea is that we project into this space, it's high dimensional, and similar things live close by another, hopefully, right? So that we get this proximity is similarity kind of property here. And really what we are distinguishing between here in these settings is word embeddings, which many people will call static word embeddings. So every time you see a mention of the word, it's the same thing, right? So this is also why we call them type-based embeddings as a cloud of concepts. And contextualized embeddings, and we'll develop those today, that show us more of this property of every time you see mention of the word, this is a slightly different embedding. We'll see what that means and where that happens here. Okay. We talked a bit about language models in the last two sessions, right? And so here the idea usually is, can you complete some form of sequence, right? Can you either fill in missing words or write forward the sequence that we have here, right? So the two flavors, so Michael talked about autoregressive language models last time, right? Where the idea is I take a sequence up to some cutoff, and now my task is predict the next word, right? And then once I have the next word that fills in the sequence, I move one ahead and I again try to predict the next word, and I go through like that. And this is a bit different from masked language models that get an entire context, say an entire sentence, and will then from that try to predict masked words, so missing words in between. And they don't have to be missing at the end, which is sort of how autoregressive works, where that end is shifting. But rather these can be masks in the middle, right? And we can do either of these, depending on our application. We may have preference for either. But these will help us learn effective language models. And then last week, you guys talked a lot about recurrent neural networks, right? So RNNs are a great way of storing context and more context. Some of the traditional models that we maybe have had before allow us. And this was the general scheme here, right? So where we had our input layer down here, you can see the cursor here, in which our word goes in, maybe in our static embedding. We have some matrix W here of weights that transforms this into our internal representation, right? Our hidden layer. I might have many of these, right? So this little arrow here says this is this unrolling over time, right? So I apply this to every word as it comes in. So I write forward this hidden layer representation, and I might either at the very end of the sequence or at every step, depending on what it is I'm doing, generate some form of output here, right? So some y hat. And truly what we are after is this hidden representation here, right? So really all the magic happens down here in the hidden part, where hopefully we have our word embedding, where hopefully we have our meaning going on, right? And if we learned a powerful model, then this is something that we can draw from. Okay. So how do we train these guys? We've seen this last week already. So we have our sentence that's unrolling like this, right? And I have my little model here represent each of these steps individually, map this into the internal representation, and this is the kicker here. So this is what was exciting about these, right? So I have this V, and never mind if V or W or U are interchanged. I think Michael's slides have them slightly differently. Every other paper does it differently. But we have these two arrows going in, right? So the meaning or the semantic internal representation of your word here should be influenced by the written word, but also by the history here that you're dragging along, right? And you're potentially dragging along a lot of history. Right? And now what you do is you evaluate, say, via cross entropy, some version of how well does the output distribution that I'm producing here match the ground truth output distribution, right? And this is what you're seeing here. So you have your true observed word y, and you have your y hat. That is the word that you're generating, right? And if you're now looking at this autoregressive scheme here, so I read she, next word is went, so I should ideally produce went, right? If I produce over, here, right? So she went to class. I am tempted to say she went over. This is maybe something I'm getting penalized for. All right. And what we do now is that our loss is summing up these partial losses as we go over time, right? So no loss, bit of loss, no loss, and so on, right? And now in order to get better at this, I need to update my W's, my V's, and my U's, right? So all these parameter matrices here in this model. And I do this based on the loss with respect to all of these operations, right? And this is where part of the problem comes in, because I, of course, these are shared, right? So my V's, my U's, my W's, they're always the same, right? At even every time step. So in order to update them, I have to unroll through the history all the way back, right? So I have to go all the way through here because my loss is sort of an additive component here, and have to drag this all the way around. Some people will call this backpropagation through time, because this is your time domain, right? So this is where your sentence flows. And this tends to be pretty expensive. Right. And because that is the case, we'll do this only now and then. So we'll bunch up a whole lot of text, right? So say a sentence or an entire paragraph, and then do one update, right? So instead of doing this live at every word that we're processing, right? And this is a bit different from having n-grams, right, that have fixed window sizes, because here still I have what you could refer to as infinite memory, right? I can do this for the entire Bible if I want to, right? So I can have a single RNN that drags the context of the first word all the way through the last chapter of a long book. It's a terrible idea. We don't do that, but it is possible, right? So we can, in principle, do this. And this brings us also to one of the limitations here of these models, where infinite memory might mean not so much memory, right? And that's a big problem here. So some concrete examples. If we train these models, right, and this is sort of a bit of a jump to pre-2013, I guess. If we train these models on Harry Potter and have them generate text, then we might get something like this, right? So this here is my prompt, right? So I'm starting with, sorry, Harry shouted, panicking. I'll leave those brooms in London, are they? No idea, said nearly headless Nick. Casting low, close by Cedric, carrying the last bit of treacle charms from Harry's shoulder, and to answer him, the common room perched upon it, forearms held a shining knob for when the spider hadn't felt it seemed. He reached the team's two. So this is even hard to read, right? So we as humans, and right, I have a little daughter, I read lots of books. This is terrible to read out, because already our internal language model starts stumbling when trying to go through this. But so these are word by word generated models, and you can see that we're generating named entities, right? So this nearly headless Nick, right? This is an actual character from the books. Great. So some nice properties. You see that you get some of the language, right? People are casting low, which is not really something that you would tell anyone, that you're casting low, whatever, right? In a sports commentary. You see all the words are there, and it's about London and great, right? Brooms and all of that. But this is not actual language, right? We get the same if we are horror of horrors, generate recipes, right? Which we can do with this. We get interesting things. So there's a casserole here made of Parmesan, but chopped coconut milk and eggs. And as just one of the highlights, place each pasta over layers of lumps. And we all love lumps, right? So anyway, not great, right? And why is this not great? This is not great because of our memory issues, right? So everything that we're doing today is going to be driven towards fixing these memory issues, right? So RNNs are great because we have infinite length. I don't have to say language has to come in 5-word units. You cannot say a thing that's not 5 words, right? That would be terrible. That's great. We have our memory, right? We're dragging along our internal representation. And we have the same weights, right? So this is great. We can efficiently update these things. But they might be slow. We have this problem of the infinite sequence. And as a consequence of that, it's really hard to use context, and especially long range context, and we'll see that in a moment. Right? Okay, so let's look at this again. If I'm updating these guys here, right, I'm going all the way through, and you're seeing that this product here, this is not a long sentence, right? But this product grows and grows. Now, if you have a long sentence there, this will eventually become a very long list of multiplications, right? And whenever we multiply a whole lot of things, there's two risks that we're running into, right? So either what these gradients here, these updates to my model, they explode, right? So they become massively large and override anything that I've seen before, right? So this is what we might call the recency bias. Recent information counts everything, everything else counts nothing. Or they vanish, right? So they become so small, you're multiplying sub-1 magnitude components over and over again, and what you get is something that's virtually zero, or you're even underflowing your data type, right? Big problem. So this leads to situations where you're forgetting everything that you've seen long distance, right? And this is what you're also seeing in these Harry Potter or recipe generations, right? The model after 5-6 words has no idea anymore what it has been doing, and then you get these things where there's phrases in there that feel like language, but the whole doesn't really read like a text that a human would write. All right. Okay. And that's really a big problem of a lot of these models that we've then try to over time fix with a bunch of follow-up innovations here that try to look into these. The LSTM, so the long short-term memory, is one of these attempts at trying to go at this. Okay. So this was explicitly designed, and this is from 97 or so, right? So it's been around for a moment. It really flies since we have a better compute and more data. But it's a model that we've seen for a while. Okay. So explicit goal here is how to handle long-range dependencies, right? And if my observation in RNNs was that I'm okay at local short-range dependency and I'm terrible at long-range, we'll have to have explicit components in here that do this, right? Previously, we had this idea of there's one internal state, a single vector variable that captures all my context, right? And I'm multiplying this thing over and over again, so my v carries over, multiplies, and carries through. Now, what we're doing here is we're having two internal variables. And one of them is explicitly, so the C here is new. My hidden state is sort of similar to what I had before. But my C here, my context, is my long-term memory, right? And I'm going to explicitly write to and read from this long-term memory. Okay. All right. So quick intuition, and then we'll look at a few shiny diagrams and see where this gets us. So we're doing things over time again. So the processing principle is going to be pretty similar to what we've seen from RNNs. And we have our hidden state and our cell context, right? And we drag these along over time again. Both are vectors. And now at each time I explicitly think about, do I want to delete things from my memory, right? Do I need to forget things? Do you need to write through memory? And do I have to read anything from memory, right? So do I have to remember, forget, or memorize? And this is great, right? So this is great because my modifications, right, to my internal state now become additions and subtractions rather than multiplications, which for our gradients is good news, right? So this means I can update at every step rather than having to go through the entire sequence when I want to make updates. All right, so high level, this looks pretty much like an RNN, right? We're going to zoom in a moment, right? But at a very high level, again, I have my inputs down here. These are my words. Right? They go in, form some form of internal representation, and I'm producing some form of output. Now, what I'm passing on, again, is not my internal state times some v, but it's two things, right? So it's my hidden state and my explicit memory, right? My recollection of what happened before. Okay. And now we're zooming in. So I'm going to show you this middle box here, right, is this box. Right, and Shudder, this looks already like circuits, so we'll have to have Kirchhoff's law in a second, probably. So let's see real quick what's going on here. Right, so high level again. Words come in from down here. Outputs are being produced up here, and I'm passing on two things: my long-term memory, my short-term memory. Right, and in here, lots of wires that go places. Right, we're going to look at these in a moment and see what these do. And again, I'm doing this over time, right? So this is my time step -1, this is my time step 1 ahead, and this is my current time. All right, so what's happening in here? This first component here, and we'll look at this in a moment, helps me forget, right? So again, this line up here, this wire that I'm drawing through, is my long-range context, right? So my long-term memory. And the first thing I'm deciding is based on the word that comes in and based on my internal state here, should I forget certain things from memory? See in a moment how that works. I might want to, again, based on the new word coming in and the internal state, make new memories, right? So really actively commit things, I will need this later. I can update my internal state here. Right, so I can now feed into both my internal state that goes out here, as well as my hidden state, and then I produce my outputs here. And so these gates here, these components here, are used to explicitly control what and how much I memorize, forget, and update. Okay, let's work through these separately, and I'm going to move my camera here for a moment so that you can see some of these equations. All right, the highlighted part here is now only controlling the forgetting, right? So I want to control what goes here into my memory, and I'm updating my memory like this. So in goes my internal state and my new word that I'm just observing, right? And what I'm doing here is I'm concatenating these two, right? Previous internal state and the current word that I'm reading, those things are being concatenated. I multiply it again with some matrix. Well, this thing here is just my intercept. So this is some form of linear regression again that I'm having here. And I have a nonlinear activation function, right? So that lets me basically push this into probability space. So what this thing does is, for each of the facts in here, for each of the bits that I have here, or the neurons that I have in here, I will now have a component in this thing. The higher this component is, the more I keep of my memory. The lower the component value is, the more I forget of that memory, right? So if I'm putting in a vector of all ones here, I memorize everything exactly the way it is, right? So keep my memory exactly the same. If I pass on the other end a vector of all zeros here, forget everything. Nothing has any meaning anymore, right? And usually you'll have something in between, right? So think of a setting where you're following along, you're already 5 steps into understanding the sentence, or maybe 5 sentences even. And now suddenly the conversation shifts, right? I might want to retain some of the general context of what has happened, but by and large, the things that I've just said are now meaningless because we're talking about a different thing, right? So I want to clear my memory here. Okay, the other operations are going to look pretty similar, right? So if I'm going to this next one, now what should I actively memorize? And so, and for that, I have my internal state here and the word that I'm currently observing. And again, the game is sort of the same, right? I'm concatenating these two. I'm multiplying them with some weight matrix that I have for this purpose. And I have my intercept here. And now what happens is this first guy here controls the strength of update. How much do I want to memorize? And this thing down here is this candidate information, right? So this is the new added information that I want to write into my long-term memory, right? So again, the way to read this here is how much of what do I want to add to my current memory? Say again? Oh, this just helps you shape things again better into sort of the negative one-to-one space.
Final signal. Like, why do we care about the negative one?
Because I think the purpose then, and I'm really just fishing here from memory, is that you can sort of de-emphasize facts, right? So you can actively stay away from parts of the information space, and that I think is better captured in the 10H. Now I'm updating, which has basically happened already, right? I'm updating my long-term memory. And this is nothing but what we've seen so far already, right? So I have the strength of my forget gate times the current long-term memory, right? So I'm decaying some of this, right? So again, if this is all ones, I stay constant. If this is all zeros, I completely clear my cache, or I do something in between. And then I update, strength of the update times the new information that I'm writing in, right? I just add these two components, and this gives me my new long-term memory, right? My new memory bank from which to operate. All right. And then finally, we are not done yet because we also need to do things, right? We were supposed to be a language model, say a word or otherwise do things. And this is our output and our hidden state here. So these things we'll have to produce at this point. And again, this follows a somewhat similar way, right? So again, I'm using my my hidden state here and my current word. Again, this goes through a linear regression with an activation function on it to produce the next word and to update my internal state. Right. So, and at this point here, so you'll see that this is the only point at which my long-term memory does anything, right? So I push into and pull out of my long-term memory so that it is updated up here. But it never influenced anything up to this point, right? So if you look down here, so the CT never really happened other than updating itself. So only in making my new hidden state that I'm then passing on, right, does this ever have any effect, right? So this is interesting. The output here hasn't been influenced by that, right? So this is the output here is influenced by last state plus current word, right? But I'm not influencing this by this long-term context. And then I'm passing this on. Cool. Does everyone see what's going on here? Because this can be a bit overwhelming, but general intuition, right? So 3 gates for forgetting, updating, and outputting our information here. This is sort of the value proposition of, in management speak, I guess, of these models and why they are interesting. All right. Now, this is great. Are we done, right? Is language modeling solved? And unfortunately, it was not solved in 97. So we've learned things since then. You'll see that even despite these explicit controls here, there is still a possibility for vanishing and exploding gradients, right? So we have no insurance against that. I can't guarantee you that this will happen. It's much less likely, though. If you think back to your RNN, we are able to carry through facts for a long time, right? But in order for that to happen, we have to sort of have this very careful balance of multiplications that sort of preserves some of the information as we go through. That's tricky business, right? So this is really like tightrope walking. Here now, instead, we have these 3 explicit mechanisms to carry through information and basically do this explicitly. And this has led to much improved performance on a lot of data sets. And we're going to look into some of these in a short moment. Now, what I want to show you here, and I'm going to hammer on this because this is sort of the part that I'm very interested in as a researcher, is trying to turn these models inside out, looking at transparency. Like, can we interpret what's going on in these models at any point? So, and what has happened here in these nice, colorful little heat map encoded texts is that we have that we show how much these individual cells fire or switch on, right, as we go through. So we can, for example, learn to become sensitive to the position in the line, right? So you see that the models are pretty out unless we are at the end of the sentence, right? And then we start paying attention here. We can turn on when we're inside quotes, right? So the cell lies dormant up until the point that I see the quotation character, and this is then when I really start paying attention. I might activate within if statements if I'm parsing program code. And very often I might be doing this, right? So I might just be sometimes on, sometimes off, and memorize some of these informations, others I don't. And I might pay attention to things like depth of indentation, or I might look for things in quotes, in comments here in program code, right? So, and this is really just to show you that these models are pretty flexible. We don't explicitly force them to do any of this, but these models discover these strategies in order to solve whatever is the downstream task that I care about, right? So if I train these models to, I don't know, transcribe or remove the commented out code, right? Then you might see behavior like this. And you'll see now that this is pretty poor interpretability, right? So this is like, okay, sure, maybe the model does this, but to what end, what's going on here? But we'll see a bunch of times now today for other more advanced models that this type of behavior is coming our way time and again, right? So we'll see a lot of times that we can already sort of foreshadow what will happen towards the end of the course when we're looking into transparency, where we really explicitly want to say, yes, okay, but where in the model, how, why, what's in there, how are these components stringed together? Okay. Let's quickly recap what we've seen about LSTMs, right? So they are very, yes, sorry.
Yes. You talk about the cell turning on about it paying attention. What exactly does that mean? Does it mean that like that the context vector is kind of more like stronger, has more ones when you calculate how much you have to remember? What is it?
Great point. Yeah. So what does it mean for the cell to turn on? Committing things into C, right? Committing things explicitly to memory. This is what I mean by that here, right? So what are the things that the cell most strongly remembers, if you will, right? And that's why this is easy to track. Yes.
So what is it? What's about when it is off? How's the relation? Doesn't like give it deep priority that much, or how, for example, when the cell is off?
Off here really, and this is maybe me using sloppy vocabulary, right? Off really just means that I don't memorize much or any, right? So depending on the heat of these things here into my context vector, right? So this really just, so if you look at these guys here, right? If there's so basically all this heat map stuff does is look at this part here, right? If this strength here is very high, you saw a lot of red. If this strength here, this I, is very low, you saw a lot of blue. And this is all this visualization did, right? So this is really just saying, okay, which parts of some input text here does this model learn to pay attention? I'm here on shaky ground because attention is going to come in a moment and it's different. But so where does the model look, and where does the model say, yes, this is the juicy stuff that I need to solve my task, and how much do I commit that to memory? Does that make sense? So if this, well, if this component here is near 0, you saw the blues.
And how does this mean, like, part is important, which part is not?
Yeah, so you have this matrix here, basically, right? So this component here is what controls the strength of this, right? Together with, of course, your current word and your internal state. So depending on where you are and depending on what's being said, you update your long-term memory, right? So that's the strategy, and it's controlled entirely by basically this one linear regression up here. And this linear regression there with its components, with its W's and its intercepts, that's what would hopefully learn to pay attention to end of the line or to things in quotations, right? Depending on the task you're setting the model. Does that make sense?
Yeah.
Yeah, but these are great questions, right? Because this is exactly the way to try and interpret these models and see what's going. Okay, good. Any other thoughts on this? Because this is helpful. All right. So to sum up real quick, these things taste a bit like RNNs, right? So same unrolling over time behavior with a few more explicit controls. That's also why they can sort of behave like RNNs, right? So if you switch all of the gates off, you more or less have an RNN with 2 memory bits, if you will. This is why in virtually all tasks, they will do equally, if not better, to RNNs, right? They're more powerful, but can default back to sort of an RNN, if you want that. They are really good at capturing long-range dependencies, so things that even have been a long time ago, we can now memorize much better. Now, this does come at the expenditure of quite a few more weights, right? So we have now 3 linear regressions where we previously had 1. And this means we need more data to fit that. We can still have our vanishing and exploding gradient problems, and of course, it costs us a lot more compute, right? So these things are more demanding when it comes to the computational resources that we need to run this. Okay. Now, we are not forced to train this stuff autoregressively, right? So there's many different things that we might want to do with these models. And we can use many different training schemes in order to represent that, right? So if our task is not complete the sequence, right, I might want to classify things. So maybe it's sentiment classification I'm after. It's one of these very standard tasks that I think you have already or will do in one of your exercises also, where the idea is, given a text, can I predict whether this is positive or negative, right? So if this is a product review, is the person happy or unhappy with the product? Or if this is a tweet about a politician, how in favor of the political leaning of that person is the author, right? So these might be your typical either classification within deterministic concrete classes, or your regression within continuous on a scale, right? Now, we can train these models for that and then use the hidden layers again. So this is our internal representation as our representation of the information, right? So I could say, let's put a whole sequence of words in there, have the internal representation, and now use something else. I mean, if I wanted to, I could even rip this out of there and say, well, now random forest, go wild on this, right? So completely break my gradient train and do this externally. And you see that people did this back then. Right? Not a great idea, but you could. Right? Much more commonly, we would put some form of classification end onto that so that we can then start reasoning on this. So the 2 big flavors that we have here are autoregressive training, right? This is exactly what we've seen so far. My X1 goes in, my magic happens here on the inside, right? My X2, the next true word is what I want to predict, right? And then I keep going through like this. But I might want to do other things, right? So I might want to say, okay, sure, my same sequence of words goes in, but I'm producing some form of other label. Right? In the simplest of ways, this could again be my autoregression, but it might be something else. So I might, for each word here, want to produce part of speech, right? If I want to label this, I might want to translate this into other languages. I might want to assign leaningness or sentiment scores for each word, or do many other things like that. Okay, but I can also play schemes like these. So I might want to read a lot of text, produce nothing here, just hold my feet still, go through, read word by word, always diligently updating my internal state. And then at the very end, once I'm done with my sequence, I'm saying, well, yes, positive or negative, or here's a translation of the entire sentence, right? So all of these I can produce there. And if I want to, I can do this in slightly different ways, right? So there have been many architectures that, for example, tried this kind of thing, where you said, okay, I'm taking the internal representations, I'm passing them on, and now I'm doing something with this. And here we have to pay attention that this doesn't become voodoo, what we do there, right? So we could concatenate these, which is a very bad idea, right? Why is it a bad idea to concatenate there? Yeah. So we're combining now these representations here, right? For words 1 through 4 here, maybe, right? And now something comes out here, right? So these might be my internal representations or my outputs or whatnot. And I'm now, according to this figure here, I'm combining this in some way, right? And then I'm making my sentiment classification. Why is this combination always going to be some form of addition, multiplication, averaging, and never a concatenation at that point? Because language, right? So nobody tells me that this is 4 words long. This might be 17 or 25, right? If I concatenate, that this guy here knows it wants 4 times the length of whatever these guys here spit out, right? So concatenation here is a bad idea, right? I need something that preserves the format here where I know, well, this is 20 neurons long, right? So what's the shape of this vector, which I can't guarantee if I say, well, whatever comes in, and then I stick as many of them together and make a single prediction over this. If you wanted to do something like that, the pretty much only way of guaranteeing that is to say you process things in windows, right? So you say 5 words at a time, next 5 words, which again breaks your flow of language, and is generally not a good idea. So in the vast majority of cases, you will some form of average these guys. Okay, now the not so surprising next step that people have been taking is, if these models, RNNs, LSTMs, read left to right, or read in the direction that humans would read text, right? Which doesn't always have to be left to right, but for us, maybe it's left to right if we read English, right? And that makes sense because this is how we process language. But there may be applications where it's helpful to read from the other side, right? The intuition here being that if there is indeed some bias of these models to pay more attention to recent stuff or to early stuff, right? And it might be good to flip the order and give everyone a fair chance, right? So everyone gets to be early or late once, right, within the sentence. And this is why I'm putting in this right to left pass, right? So this is what we've seen so far. Inputs go in, are being encoded, hidden representation outputs, right? So a bit simplified just so that we see what's going on. And we're reading left to right. But we are doing the other thing as well, right? So we're reading the same sentence, exactly the same input here, from last word to first word, right? And again, have our multiplications, right? Or if it's an LSTM or explicit forgetting and remembering. So I'm just rolling up the content from both sides, right? And this again helps me cover some of these maybe some of these limitations that some of these models have. This is also, so this is really a band-aid, right? Does everyone see this? This is not in terms of information processing as people do it, right? No person does this because we reason differently, because we don't understand properly how humans reason. This is why we make these models perform this klutchy way of doing things, right? So you'll see that some of the more advanced models that we're looking at, they stop doing this because you don't get added benefits of this anymore. So the entire reason for doing this is our models suck, and because our models suck, we make them suck a bit less by giving them sort of an access towards the end of the sentence early on, if that's helpful. Okay, and now what we're doing is what comes out of these hidden representations here, right? So my hidden representation at having read only the leftmost word and having read only the rightmost word, and the rightmost followed by the next and the leftmost followed by the next. I'm concatenating those, right? So this is really just, so this guy here and this guy here, sorry, concatenated. The second one and the second one concatenated, third and third concatenated, and so on, right? So meaning by concatenating these, this new vector that I'm deriving here is the vector that represents this input. but contextualized either in nothing, start of sentence, or contextualized in having seen the entire sequence already here at the other end, right? And this gives me this beneficial access to sort of a long-range view from all the way from the back to the start on the situation, and a very local view of, well, this is where we started, right? So this is where everything's still pretty fresh. And you can already see that this is really just meant to fix some of our memory issues, right? Yes.
So
Yeah.
What kind of things they read? Like they have two bidirectional and then concatenate. So first, what exactly they read, and then what's the purpose of having this kind of mechanism to have read bidirectionally and then
So can you give me a bit more context to the questions of what exactly do they read?
Like why we have, for instance, this way, why we have two-way, why we're reading it like kind of bidirectional.
So imagine the sequence is long, right? So this is not 4, but imagine this is 20 words or something. It's a long sentence, and imagine it's a news story, right? So you're early on saying Microsoft acquires some other company, right? And then there's more information going on, right? Once you, in the traditional scheme, right? So this is the world of just LSTM or just RNN, right? So prior to bidirectionality. Now, in that world, it's possible that if Microsoft is not being mentioned anymore, right? Afterwards, it's just called the corporation or whatever, right? You might forget the fact that Microsoft was there, right? So by the end, so you are here at word 25, and maybe at the very end, you want to predict something, right? It's likely that you've lost the fact that Microsoft was there, right? Certainly in RNNs, maybe also in LSTMs, right? If you forgot key bits of information. Now, so there's nowhere in this latent space of this model at x25 here, is there any explicit trace of, say, Microsoft or some other early information in there anymore? So that's a problem. So now that means that this model is going to perform poorly at this task. Now, what you could do to repair this is say, we need better memory. We need this thing to properly understand text. Well, it's really hard because we don't know how to do that. Now, this is why I call this a band-aid, right? A quick and dirty fix is to say, well, you know, if I turn this sentence the other way, right, I completely break grammar, but that means that the very last thing I'm going to read here is this word, which is Microsoft. And now it's really fresh in my memory, right? So now I have a very recent, very fresh representation of Microsoft, this entity that might have got lost here in this reading of the sentence. Does that make sense for the motivation of why we want this?
Like the read first and then we read from the beginning?
No, there's no first and after. So this happens at the same time, right? So the idea is really just that traditional models would do this one, right? And if you do this, then early stuff is far away, right? By the end here, by this last representation, you might not have this anymore if stuff went wrong while memorizing. Now, if instead you would do this, right? So imagine you don't do this at all, right? So you just read the sentence the wrong way. That means that in this case, you end on Microsoft. It's really fresh in your memory. And if your task somehow needs memory of the entity Microsoft, you now have that. It's fresh in your memory, right? Because you read the other way. The very most recent X here that you read was this Microsoft, this word that was at the beginning of the story. Right? It's really just the first word that you arrive at the very last moment if you read from back to front. Exactly. So it's exactly, yeah. So we start at the end of the sentence and read to the beginning in this red one here. And this is what this tries to fix, right? So this is really, I mean, it's almost stupid, right? If you look at that, right? This has nothing to do with artificial intelligence and mimicking anything in anything, right? No actual organism would do any of this nonsense, right? Let me read that text twice so that I remember the beginning better because I ended it, right? This is absolutely mind-boggling. But it gives you these two alternative representations. You do this at the same time, right? So you have one read like this and one read like that. And you glue these together. And by having both, you have a better chance of having somewhere retained a recent memory of stuff that was early or late. Right? Okay, yes.
But you cannot do it at the same time word by word, right? You have to do it in sort of chunks. Because like you cannot calculate the hidden vector concatenated for word one and word one in blue and word one in red.
No, these are separate processes. This doesn't happen in the, so these are really completely separate data structures here. That's exactly right. Yeah. So depending on what hardware you have available, it might happen in parallel, right? But these don't share the same memory bits, right? So you produce these in parallel, and then you glue them together such that you have now this new Frankenstein-esque representation here that is bigger, right? So you've done twice the reading, and now if these are 5 long, right? So this thing is going to be 10, right? Because you stack these up, right? So this is now the sum of its parts. All right. And now you use this thing here to produce your outputs, like you did before. So previously you would produce your outputs, right? Your predicted y hats here out of here. And now you do this out of this stacked representation. Okay. This was surprising. When this came out, this is more recent, right? So this was a 2016, 17 or so paper, because reading the other way really doesn't make any sense, right? So a lot of people who come at this from a linguistics point of view, right? This is really just not what you do. And this is why it took us so long to come up with this really simple fix, but it works extremely well, right? So for a lot of tasks, this is really completely what flipped around state of the art. And the problem here really that we're facing is it's of course slower, right? We're doing twice the work, and it in the end then becomes bigger. So that's a potential issue, and we cannot always do it, right? There are tasks for which the end of the sentence is simply not available, right? So if you're doing your language modeling task and you want to complete the sentence, you don't know the end, right? So anything that's autoregressive, you're not allowed to do this. If your task is translate the sentence, sure, that's fair game, right? Because someone gave me the entire sentence to translate, and I can read this any which way I want. Yes.
Say that, so the main goal here is to not to forget the first thing that we mentioned, right? The earlier things that we
All the late things, yeah.
So how about if we have, like, for instance, start with something like, I don't know, there's a company name, and then in the end, we already we're talking about something else. So in this case, we will have like more work to do, but for nothing.
Yes.
It feels like kind of, I don't know, like noisiness in the model, or kind of, I don't know, less performance.
I mean, sure, there's definitely situations that you can construct that will be like that, right? If you know that never does. So if you were to construct a situation where early content never matters,
yeah.
Right? So say you do a whole lot of lorem ipsum for every sentence, and then at the end you say, by the way, the answer is 1. Right? So where really, truly the label is the last word, right? This would be a terrible, terrible idea, right? So you do a whole lot more for nothing gained.
So we need to know for what purpose.
No, well, but you don't, right? So, and in reality, language is not like that, right? So since we want general purpose language processors, this tends to be a good idea in language because language tends to want context, and this is really just one way of fixing these long range dependencies. But yes, you're dragging. I mean, the game we are often playing with many of these is because language is such a nasty beast, right? It's a thing that's not developed as an artificial information processing tool, right? It's really just how we evolutionarily discovered communication with ourselves and others. Reverse engineering this is tricky, right? So things that come out of evolution are always really nasty to represent in computers, right? And this is what we try to do here, to try to throw the whole kitchen sink at this problem. Hopefully one of these many components, right? Because also remember that in here, potentially there's an LSTM every single time, right? So potentially every single time I'm doing this whole thing of what do I have to memorize, what do I have to forget, right? So all of these considerations with thousands and thousands of parameters here happen at every step. And then I'm saying, oh, because it's still not quite working, let me read it the other way as well and slap that on top, right? This is not elegant.
Yeah. Practice, I mean, is there any way other than trying to know which model works better? Like, for instance, if we have a look at the data, I don't know what purpose could be like very large. So testing could be the.
Yeah. I mean, at the end of the day, it's empirical. You can, of course, make educated guesses if you know that I'm in a very constructed language, or it's a programming language maybe, and the convention of the programming language is such that this will not have. You can make guesses on this, but really the proof here is usually empirical, right? And this is where empirically these models for actual language that is not constructed to trip it up, right? It tends to be the case that these models work better than the simpler versions, because they can, in some ways here, they can learn to ignore this part, right? So imagine that this is always useless, right? Because we're in your constructed world. I still have this matrix U probably up here, right? That produces outputs from that. And that can very well learn to just never look at the red stuff because it's always useless. I did more, it's expensive, but it wouldn't hurt performance because I can learn to completely ignore this part, right? So I take a lot of nodes, if you will, and then I burn them. I'm allowed to do that. These models have the capacity. And this is why these tend to be strictly better. They're strictly better at the cost of more computation, right? And this is usually the game we play. We have a lot of models, if you look over time, right, over decades, if you will. A lot of models have these very diminishing returns, right? So you have a pretty simple model that gets you 80% of the way there. The next 10% then take you 2 orders of magnitude in complexity of the model, right? And now you're at 90 and so on. So we really piecemeal, we get closer and closer to the goal, but I'm not sure that we ever really arrive at being perfect at this. Right? But this is a perfect example of this, right? So we're doubling complexity here of this, plus then some, right? So this is more than twice as expensive computationally. So that sometimes it helps, and sometimes we'll ignore it completely. Right. Okay. Now, since that's the case, why not make it more complicated? All right. So here, again, our intuition is that what we do with these hidden layers here is enter abstraction, right? So on this level here, we just model word identity, right? So this is, I'm the word, cat, sits, whatever, right? I run this through a transformation to get to some internal state, right? So I perform abstraction to hopefully retain meaning, semantics. Michael would hit me for this, I don't know, right? For me as a computer scientist, meaning, right? So we hold meaning now, that's great. And if abstraction gets us meaning, computer scientists like to have more meaning, right? So we could put in an extra way, an extra layer of doing just the same thing again, right? So I have yet another linear regression in between here, and I pass these states on as well, right? So and every time my input is now not the raw word like here, but it is the previously encoded state already, right? And I can play this arbitrarily many times. So if you think back to your ResNets or similar things, right? So these large models for computer vision, they work in some ways similar to this, right? Where you have pixels here and noses and maybe rhinoceroses or whatnot up there, right? So from broad but meaningless to narrow but pretty semantic sparing, right? That's the idea here as well. So I can combine these raw words to higher and higher order semantic concepts, hopefully. At some point this ends because there's nothing gained anymore and I just keep juggling my semantic units here in order to then get pretty good at a task, right? And then I eventually, when I'm happy with this, I put my output layer and I produce outputs. So stacked LSTMs or stacked whatever models, right? We can do this with anything we like. Yes?
Can I give us a simple example of this with translating English to German? What kind of benefit we will get out of this? If we add more to the layer to generalize or abstract.
So imagine you have a setting here where you have a bunch of concrete words. And at this point here, you pretty much only know I've now seen these 3 words, right? So your best possible representation here is if this thing could memorize the exact sequence, right? That's sort of what's going on. But what you might want to do here, right, in the higher level abstractions might be something like, oh, this is someone making an argument, right? Or someone claiming something, or someone throwing an insult at someone else, or something like that. So these are possibly, and I can't claim that this is exactly what's encoded in there, right? Because it's tricky. We have a very hard time bringing introspection to these models. But you want to sort of cook up from the atoms, surface form words, to meaning of those words, to meanings of higher level units of these words, more abstract semantics, right?
I'd like to add another.
Say again, what?
Like we say, we catch the abstraction meaning of the words so that we can match from the abstraction to more words than this.
Yeah, to our outputs, right? So if you want to translate, and we'll get to that argument in a moment when we look about attention, but if you translate text, you never say, okay, I read this word means that. I read that, you as a person, right? I read that word, this word means that. It's not the case, right? So you read the entire sentence, maybe even more than the sentence, and then you go back and translate the entire sentence, right? So we do this all in memory. There's no sequential nature in it, ideally, right? And this is sort of what you're trying to get at here, poorly, crudely. Next step is going to be to do this slightly better, right? But that's sort of the intuition here. More complexity, more abstraction, hopefully gets you richer semantic representations. Okay, this brings us to the last model before we'll have a little break. And this is Elmo. So there's this whole family of Sesame Street themed models, right? And Elmo was the earliest one, and then all hell broke loose. And then we have now every Sesame Street character somewhere in our model family. Okay. And this really puts everything together, right? So we want very rich embeddings that capture words and really word types, right? So these are static embeddings. Every time I see the word dog, it should be the same representation. I want then on top of that context bidirectional, right, from both directions, and I want to stack my abstractions here. So it's going to be 2 layers in this case. And now I want ideally the ability to then fine-tune this for arbitrary tasks. And this is what gives you this beautiful zoo of Elmos here, where let's stick to, right, my raw words are embedded. This might be your word2vec or something like that. I do my stacked autoencoding from left to right, and I do my stacked autoencoding from right to left. All right. This gives me these guys. I can now concatenate on all levels, right? So I have this word. Well, I don't need to concatenate much there, but I can to preserve shape here. Now I can concatenate on this level. I can concatenate on the top level. And I can now basically still weight these, right? So I can again learn which of these parts here, either this way or that way, I want to pay most attention to. And I can use the product of all of this, right? So the end of this, I can put through a final linear regression or something in order to make decisions. So this was the scheme that was called Elmo and that started this whole Sesame Street madness. And if you look at this here, so this was state of the art before Elmo entered the stage, right? So never mind what exactly the scores are, but higher is better. They run from 0 to 100. And these are large data sets with many different tasks. So it's a general language understanding and language processing set of baselines. And then if you look at your baseline performance here, which tries to model sort of this, right? In our world, it's sometimes a bit hard. If a paper says 53%, it might be hard for the rest of the world to also get to 53, right? So it might be a reality where you get somewhere there, right? But there's some seed selection or otherwise magic going on here that gets you sort of there. But our best attempt at rebuilding these papers and what the original papers claimed, right? And now adding on top of this baseline, so doing the same thing, but adding Elmo to it, right? And you see that you get drastic improvement. I mean, so in our world, this is massive. So having between 5 and 25% relative improvement is incredible, right? So we are fighting over 1 percentage points, right? That's a paper that you can publish. Having 25% is insane, right? So this is this was 2017, 2018 when this all happened, right? And this basically for a while, for a half year, everything was Elmo driven, right? So whichever task you wanted, so machine translation, classification, regression, everything had this family of models under the hood. Okay. So great contextualized embeddings at the cost of lots of training data. And really what the show does was have more complexity, right? Give it more flexibility, read left to right, right to left, lots of abstractions. And if you have enough data to power this type of model here, you'll get pretty good results, right? This is also going to be sort of the spirit of some of these models, right? So around this time, we see lots of different applications that are like that, right? So we see the first occurrences of token-based representations, right? Contextualized in the neighborhood of their occurrence. And we'll look after the break more at this. Or localized type-based ones, right? That says, okay, where every time I see a certain word, it should be the same thing, right? All right. And I think the other powerful property of this was that you could pre-train these models, right? So if you run Google or some other large corporation, right, you can pre-train this stuff, give it to the world if you want to, or keep it as a trade secret. And now everyone has the same quality language model and can fine-tune that for do my homework or whatever it is that you guys want to do, right? Okay. Good. So attention. We're going to take a 10-minute break. So 1:15. I would say we'll get back, stretch your legs, open some windows, and then we'll look at the second half of the class when we're looking at attention, self-attention, and transformers.
I have a more general question. You're also responsible for the modern search engine.
Yeah, that's right.
I couldn't participate in the last weeks, but now I have a free slot, so I would love to participate. I already did the second exercise,
Okay, yeah.
but I couldn't do the first one. But I know it's in the grades, but I hope it's still possible for me to participate.
Absolutely. Just come by. So it's you know, right? It's this afternoon.
Yeah, and the tutorial as well. I don't know if I can participate. Is it really important, or is it like?
No, so we in the tutorial for that one, we don't cover any new material.
Okay.
So it's really only trying to do the homework with you, or if there's any questions about
Especially
the
because the presentations are due sometime, and are they in the tutorial or in the?
they're the main session.
Okay.
So there's never going to be any. I mean, again, it's helpful,
Yeah,
right?
yeah.
But there's never any grade relevant components that are only in the tutorials.
Okay, perfect.
So just come by.
Okay, yeah, I will. As I said, I already did the second exercise. And
Excellent.
I also have a question. I looked at your website and at the papers you had, and I'm looking for I don't know how it's called, Laborpraktikum.
What
Ein Laborpraktikum.
Labor-
It's like you need
okay.
to do practical.
Wir können das auch auf Deutsch machen.
Okay.
Das ist also für den Rest.
Ja, Laborpraktikum, weil ich Kommunikationswissenschaften studiere, Master. Und deswegen, ich habe das jetzt angeguckt, es würde mich sehr interessieren, am meisten der Teil, warum überhaupt die Sachen so sind und das besser zu verstehen, die ganzen Modelle. Ich komme auch aus der Informatik.
Okay.
Deswegen, AI hat mich schon generell immer interessiert.
Ja.
Und ich habe auch schon Deep Learning gemacht, Computer Vision und so weiter. Und deswegen wollte ich mich dieses Semester auf Language Models fokussieren.
Super.
Und ich wollte fragen, ob vielleicht es möglich wäre oder überhaupt was für Themen ihr gerade im Moment bearbeitet.
Ja.
Oder die Richtung auch Laborpraktikum.
Absolut. Also wir haben relativ viel die Richtung. Ich würde sagen, wenn Sie mir eine kurze E-Mail schreiben, damit das nicht verloren geht in dem ganzen Ding, dann wäre das super. Aber wir haben viele Themen, die so sind. Ich habe jetzt das Laborpraktikum als solches noch nicht gemacht. Deswegen, da müssen wir mal gucken, was das genau, wie viele Stunden und was auch mal die.
12 CTS-Punkte.
Okay, das ist schon relativ.
Und soweit ich weiß, kann man es während des Semesters machen. Man kann es aber auch sonst verschieben. Hauptsache es ist halt Leistung erbracht. Also man weiß das von anderen Kommilitonen, dass sie es auch teilweise ein Stück gemacht haben während dem.
Ja, super. Nee, also machen wir unbedingt. Also schreiben Sie mir eine kurze E-Mail, dann suchen wir uns einen Slot, wo wir ein bisschen besser drüber reden können. Aber wir haben relativ viel so in dem ganzen Transparenz, Erklärbarkeit, mechanistische Interpretationen und sowas Bereich. Da machen wir dann was Schönes.
Ja, weil ich finde es generell interessant, weil diese AI-Sachen, das Programmieren und so weiter ist ja das eine, aber mich interessiert halt dieses, wie kann man es verbessern, halt, wie kann man es besser verstehen und auch deswegen wollte ich auch Kommunikationswissenschaft studieren und nicht eben Machine Learning, weil ich die andere Seite auch interessant finde, sondern nicht nur das Technische dahinter, das Empirische.
Ja.
Und dann habe ich noch eine kleine Anmerkung bei den Papern.
Ja.
Ist der Link falsch? Da kann, also ich habe drauf geklickt und bei mir kam halt Link not found.
Wo haben Sie das denn schon her?
Ne?
Ich habe das noch gar nicht eigentlich teilen wollen.
Da sind Paper auf der Website. Und teilweise sind
Oh,
Ja, ja.
auf unserer Website. Ach,
Genau.
ich war gerade schon bei unserer für die Modern Search Engines. Ah, okay. Das ist gut zu wissen. Muss ich noch einmal.
das ist, ich weiß nicht mehr, welches es war.
Ja.
Mit dem
War von den 24.
Genau, es war in dem ersten. Das war das hier. Also eins davon hat nicht funktioniert. Was auf mein.
Nö, ich schaue nochmal durch. Das ist gut. Manchmal vergesse ich dann was.
Weiß jetzt nicht.
Top. Nee, das ist super. Alles klar. Aber dann machen wir das so. Dankeschön. Ja, super.
Few questions.
Yeah, sure.
First one is about organizational stuff. So, do I need to be signed in somewhere so that you know that I take this class? Because there's some.
The answer is probably yes. But
Yeah.
so we have this Moodle page. Are you aware of that?
I know that it exists, but I don't think I'm signed in. So I need to sign up there. Right?
Yeah, I think that's probably the best way of doing things. So I don't know, Svenja, do you know the whole registration Moodle enough, or do people have to do more? Or maybe actually you guys know this better.
What are we talking about?
Registering for this class, Moodle is Moodle what you?
For the exam and.
Okay, good. So is it Moodle? Oh, yeah, this is all a mystery to me.
Yeah. That's the first thing. Second one, like passing the exam is a prerequisite for passing the
That's right.
exam, but it has to be passed.
That's right.
Like not the cumulative sum, but rather
It's a cumulative sum, but gated.
And then the last thing about I missed the difference between the Elmo and the stacked bidirectional LSTMs. Was it the difference only in the inputs that we given into the?
No, there's no difference as such. Elmo is just a way of combining a lot of these tricks into a concrete product, if you will, right? So it's really just taking the bidirectionality, the stacking, and some of the ways in which we then put like our inference layer on top that we call Elmo. But there's conceptually no difference there. So Elmo is an engineering contribution and not a method contribution, if you will.
But they all use some sort of embeddings.
That's right, yeah, and on the lowest level, you would then have your 2013 word-to-vec or glove or something like that, right? So you start with static embeddings, and then you model context as you go on top of
How did you do it before? Like,
Really?
because they didn't really have like word-to-vec embeddings, right, in 2013 or anything like that. And LSTM came in 97.
No, yeah, word identity. So you would usually just say, well, this one hot vector is dog and that other one hot vector is cat, right? And maybe you can learn a bit on top of that, but no, this was not around. So 2013 was a good year.
All right.
Yeah. Yeah. Well, I have to have a word with with the people. Thank you. This is super.
verschoben, da wo der eigentlich gespeichert worden ist. Oder so.
Ja, irgendwie sowas ist das. Manchmal ist es so, ich glaube, bei dem Paper war es so, dass ich das schon reingetan habe und dann habe ich festgestellt, dass ich, weil ich dann oder so Co-Autor war, dass ich die letzte Version davon nicht hatte. Und dann dachte ich so, jetzt ist schon live, weil dann geht der Pointer ins Nirgendwo. Aber Dankeschön, das ist gut. All right, folks, let's attention, huh? Let's get back to it and see what this is all about. There we go. Now, what we've done so far was lots of gymnastics, most of it sort of arithmetic gymnastics, to manage context, right? Long or short range. Now, what we're going to try and do now is try to explicitly model how much I should be influenced by all the different things that have been said before in producing the next thing. And this is exactly this intuition that I gave you before, right? When we as humans translate a sentence, we don't do this word by word, right? Depending, irrespective of order. So we form our internal representation of the entire thing, and we translate the sentence and might focus on different parts of it as we generate individual words. And this is sort of what we're trying to cover here as well, right? And this is in neuroscience and psychology, these concepts have been around. So people have been reasoning over the fact that that probably there's an explicit relationship between like different words, and it might be a weighted mixture of these different words as I'm producing the next one. Okay, so imagine this, right? The brown dog ran. I again do all my encoding magic, and now wouldn't it be nice if someone gave us this, right? So if someone told us, look, 0.4 of your attention, of your overall volume of attention in producing, let's say, the translation of the should go here, but you want to, in order to translate the best possible the, you should pay a bit of attention to brown and ran as well, and not so much to dog, right? That would be great if someone would give us this. And now we're going to try and do exactly that. So we'll now have two components. We didn't really explicitly talk about this, but so many models will have explicit encoders and decoders, right? And really, for all practical purposes here, could you close that one window still, because I think yeah, thank you. For all practical purposes here, encoders are what takes us from the input to some maybe complex internal representation. And decoders take that encoded representation and do something with it, right? Generate output, produce a classification label, things like that, right? So the game we want to play here is, as I decode, I want to pay explicit attention, right? So different degrees of influence. I'll draw from these different steps here, right? And I'm going to do this via a separate component, right? So there's going to be a separate little neural network that tells me, given a hidden state, so the encoding of the word the, let's say, and my decoder state here, where I'm starting to now generate a translation of the sentence maybe, can I estimate how much attention I want to pay, right? So it's a supervised learning problem. So I have a separate thing here that says, okay, given that you've read this already, and given that you've written this much already, how much attention should you pay to this word here, right? And I can switch this through, right? So I can do this for the first word, for the second, for the third, for the fourth, and this eventually gives me maybe a table like this, right? So these are raw outputs now of my neural network there. So the pretty obvious thing to do is run this through a softmax, and now I have something that sums up to 1, right? So I have this nice vision of these scores that I gave you up there. I hopefully have something that behaves a bit like that. So I can learn to pay attention to different parts here. And now what I'm going to do is I'm going to use all of these guys here and these attention weights that I learned in this way, right, to form what we'll call a context vector. And this context vector here depends on this, right? So remember, I used the current state of my decoder, right? So maybe I'm at the very beginning, so I've only decoded sentence start, right? And now in order to decode the next word here, I'm using this guy with this nice dedicated neural net here, right, to estimate these scores. And now these scores become these attention weights here. So now that means I have all my inputs, and I've learned, conditioned on this guy here, how much attention to pay to these to get them all into one context vector, right? So this is just some form of weighted sum. And now as I produce my output here, maybe I'm translating this to French, right? I'm now concatenating my internal state. This would have previously been the entire thing, right? So previously I would have just said, okay, this is my internal state. And based on this, I'm producing the next word, maybe autoregressively, right? From sentence start to translation of the. But now instead, I'm giving it also the context vector. So this means that the decoding here has access to the entire input sentence, right? This is powerful. I now don't have this problem anymore that I have to explicitly drag everything through RNN style or LSTM style, right? So with this now, what I can do in a moment is say, okay, at every point in generating le, chien, brun, and so on, I always have access to this context vector specific to where I'm here, right? So weighted based on where I'm already in my generation, and paying attention to all inputs, right? And this is powerful, right? So this is great because now I don't have this problem of catastrophic forgetting anymore, where things are so far away that I don't have them anymore because I'm allowed to look, right? So I'm going back. So previously the idea was always, okay, memorize the sentence. Now I burn the sentence reference. You have only your memory of it, and now generate something. Right? Here I'm allowed to read, right? So I keep the sentence. I'm allowed to look back as often as I want, and I have my explicit estimate of how much I should look at all these individual places, right? And this gives me my context vector. And this is pretty powerful. So this is just for reference, once more, all the steps, right? From our inputs here of the encoder sentences, the decoder state, to the scoring, the softmax attention weights, and then finally this weighted sum, right? So there's nothing else but one slide view of this animation there. Okay. And the thing that produces our attention scores here doesn't have to be a straightforward neural network, right? It could be anything else. So on a high level, right, we have our encoder, we have our decoder state, we have some form of attention function. This gives us a score. So this we do for all of these. But we can do this in many different ways, right? So this could be a dot product. I don't even have to learn anything. I can really just multiply them if I want to. And I can also have learnable components, right? So this could be some bilinear combination with some weight matrix, or I could make this a full multi-layer perceptron, right? So this could be a neural network of arbitrary complexity if you guys wanted that, right? So this is either a sort of co-occurrence-based or learnable way of figuring out where to pay attention. And this is, again, great because I'm a transparency guy, right? We can use this for understanding our models, sort of, right? So there's a tiny little jihad waging around whether attention is explainability or not, right? So there's a paper that says, so everyone has been doing this, and we'll look in a moment at what this is, but for interpretation, right? And then people have published attention is not explainability or interpretability. And then the next paper was attention is not interpretability. And I think there's even a third one with yet another not in there. So people are somewhat discussing this, let's say. But what's going on here? What we can do is, in producing the English translation of this French source sentence here, I can now, since at every point, right, so in translating the article here into the English article, I pay attention to the entire French sentence. right, in different degrees. And now, since I'm already doing that, I can also plot this, right? So I can force the model to just print this out here, and I get this nice matrix. And we see that we have this very strong diagonal. So brighter colors here are more attention, right? So black means I don't pay any attention, white means I pay a lot of attention. And we see that this sentence here is more or less the same sentence order as the English one I'm producing, right? So in producing the article, I read mostly the article and hardly anything else, right? In producing agreement here, I read mostly the French word for agreement, and so on, up to the point where I reach here this European Economic Area, which is turned around in French, right? So I have the area economic European, right? And we see then this pattern being turned around. So European here at the end of the French phrase is what really influences European, and so on, right? And this is what I can visualize here. And this is interesting, right? So this now finally gives me an actual view, not just a sort of kind of view, into what the model has been doing. There are, of course, more components in these models, right? There's more going on than just attention for now. But it's great, right? So here I really get a view on where did the model look in saying this thing, right? And this kind of metaphor here has been used for a lot of different things, right? So it's first of all, it's a good idea empirically, right? I'm not going to bore you with too many of these numbers, but if you want to look into these slides, so you see a lot of numbers in the mid to high 90s here, right? So a lot of these constituency parsing tasks, right, where you want to have some form of dependency parsers of trees that are somewhat cumbersome to make, right? These models get pretty good at this, right? This is interesting. So we are able to understand syntactic structures pretty well. But we can also use this for images, and images I think are really powerful. So I think this is something that comes from the text world, but actually really it lives better in the image world. Now, what's the setting here? I give you an image, and you're supposed to caption this image, right? To generate text describing the image I gave you, right? So this is what we train a model for, and of course it's multimodal, so there's some complexity to it, but it uses attention somewhere, and we can now again put these highlights here, this heat map of attention over the input image. So I give you this image here. You're generating a woman is throwing a frisbee in a park. And while when you wanted to generate frisbee, where did you look? You looked here. All right, that's interesting. And if we're saying a dog is standing on a hardwood floor, right? It's not really standing, so maybe here there's still some work to done, but dog is pretty good. Stop sign, pretty good. A little girl is whatever sitting on a bed with a teddy bear, right? This is great because there's two people sort of potentially in this picture. We're paying attention to the right one, right? But this sometimes also goes wrong, right? A large white bird like this one here is standing in the forest, or this woman holding a clock here, right? What else do we have? We have this nice little pizza here, and the surfboard is sort of arguable. Oh, okay, this is maybe not the board. But yeah, you're seeing what's going on here. So this is really helpful, right? First of all, it's a great tool for making these models stronger, better, right? Because it makes away with some of these problems that we had with forgetting with long-range dependencies by saying, okay, you always get to look. Of course, within whatever your encoder frame of reference is, right? So again, if you're doing silly things with very large inputs, right? You want to read Harry Potter again, you're not going to remember last chapter with these things. Oh, that's harder. But within sentence or maybe even within paragraph, if you're lucky, you can now explicitly look at things and influence your decisions from attention here. And as a byproduct, you have this. And this is really fantastic, right? So this is the first real time other than fiddling with the inputs and seeing what the outputs do, right? Which is terrible. And we'll do some of that, but it's bad. This now gives you a vehicle of saying, okay, what happened in the model really? Where truly did the model base their predictions on? And this is especially interesting because we're in this game of throwing kitchen sinks at problems, right? So we try to have a lot of model complexity to capture the richness of language. And here via vehicles like these, we can really see what's going on. And very often this helps us discover spurious correlations. We'll talk a lot about those when we're doing transparency, but for example, if you're classifying dogs versus cats, right? The strongest feature, does anyone know? Did I tell you guys already? So photos of dogs versus cats, right? What's the strongest feature in doing this in images?
A color.
A color, yeah, in some ways, but I'm aiming for something slightly more specific than that.
No.
Say again?
It knows.
The nose, yeah. So the muzzle or the ears, right? That would have been my guess. So I'm not a cat person, but I thought, yeah, clearly they look different. We as humans do this task. No, it's the sky. If outside, then dog. Cats are not outside. Yes, exactly. Wow. And these, yeah, no, exactly. Wow. Yeah, no, me too. Because really these all we see prior to using these techniques is, oh, the model is 98% accurate at doing this task. It must really understand cats versus dogs. No, it's just we are stupid and we are only taking photos of our dogs outside and of the cats indoors. Right. So it's really these spurious correlations, these things that give you an unfair, really good statistical advantage without understanding anything, right? We trained a model that understood nothing of the task it near perfectly solves. Super interesting. And this is really hard to figure out. I mean, you need some detective spirit and some human creativity in order to infer that that is the problem if your collection is biased like that, right? This kind of stuff here helps us see examples, and that's crucial as these models get more and more complex. All right. We have, yeah, my pointer is not visible. This is poor user experience. I apologize. I'll try to point more with the cursor. All right. So far, so good on attention. And now we're turning this thing onto steroids, right? So now we're doing attention for grown-ups. Okay. Now, so here's the deal with I think lots of word embeddings, right? Word meaning for us as people is highly contextual. For a lot of these models, it isn't or wasn't. So if you look at 2013, Word2Vec and friends, if I say the shirt is green or the recruits are green, inexperienced, right? Or green policy has wrecked the economy, where green then means environmentally aware or environmentally friendly policy. This is all the same green to these models, right? So green always means exactly the same thing as the same vector in space. To us, we read these very differently. If we are privy to whatever the agreed upon meaning is of these greens in these different contexts here, we read these very differently, right? So down here, this or this has nothing to do with the color green. Okay, so how do we tease all of these apart, right? So, and like we did with standard attention already, maybe, the idea is to put like the contextual meaning in there already when we represent these, not just when we use them to produce things, but already in the representation. And this is new about the self-attention. Okay. This is going to be the high-level scheme, and then we're going to look into some of the ways in which we get there, right? So we transform each word, hopefully have rich abstract representations of meaning. And now what we want to have is some form of weighted sum of the other words in the sequence, right? This is what we've seen so far. And really what we want with this is we want to have this explicit influence of the neighbors already at representation time, right? So the meaning of a word should be in its compatriots, right? In its neighbors. It should not be I use all your neighbors when I do something with the word later on, but really I want to squeeze this into the representation. And ideally we want positionality, and I'll show you in a second what I mean by that. Okay. So what we're going to do, and this is going to be, so think with me here, this is the moment to be really awake because this is potentially a bit involved, right? Who has seen transformers and self-attention before? Who knows how it works? Queries, keys, values, and all that. Yeah, sort of. Okay, so breathe through this with me, right? So we're going to do this slowly and be brave, ask questions, right? So because this is easy to misunderstand. We're going to go really high level, and then we're going to step-by-step zooming in into some of these components. So really high level, what we want is this, right? I want to go from a sentence for some sequence of words here to embeddings, some magic box that we're going to look at in a moment, right? To better embeddings, right? I want great representations here. these here might not be contextualized. I want contextualized representations where the embedding of the already carries with it a lot of brown and dog and running and all of that, right? So I want to load lots of meaning from the sentence here into here so that I have the best possible thing that captures, let's say, dogness, but especially dogs when they're brown and run, right? Okay, so that's our mission here. We're again going to use this attention scheme, right? So far, so good. So I'm going to do something that sort of resembles the attention we had so far, where I'm going to load weighted parts of word meaning into this new meaning of my encoding for the, right? So that's going to be my Z's here, the overall goal. Okay, my A here is just a weight, right? This really just tells me, okay, pay 0.8 attention here, right? In order to get there, we'll have to do a bit of arithmetic heavy lifting in order to arrive at this weight and what it is, right? But at the end, right, once I have this, again, some work to be done here, but at the very end, it's really just a linear combination, right? So really, the entire magic happens before, and at this stage here, we'll really just say, okay, take 0.8 of this, 0.1 of this, 0 of that, and maybe another 0.1 of that, right? Sum that up. Yes.
I was having like attention to self, so attention of that to that.
Well, this is attention. Yeah, so good question. This is actually crucial, right? Because otherwise you would say you're not allowed to think of dogs when representing dogs, right? When we're at that point. So you very often will see, so think of that French-English heat map, right? So you will have that strong middle diagonal, which means this connection here is going to be a very strong one. Once we are generating Z2, that connection is going to be strong, likely, because that means the local meaning of the word you load in with some degree, but you also load in some of the other words, right? But that's why it's, I apologize about that. So that's why you will always have, and pretty significantly probably have that local component, right? For the representation, stronger than maybe in that English-French example where we were producing already. Here we're just capturing meaning at this point. Alrighty. Now, here comes the magic. So in determining this weight here, I'll have 3 components, right? So I'll have 3 neural networks that help me do these things. I'll have queries. We'll talk about it in a moment, what they do, right? So queries, keys, and values. All right, so it looks something like this, right? So for the here, I have my local embedding. And now I have some other vector Q for the query, K for the key, and V for the value, right? And now what we're going to do is we're going to go through this and via these queries, keys, and values, get to these strengths of association that we want to arrive at, all right? Okay, so high level, I'm representing V here. Now I want to say how much attention should I pay to the local word the. This is, I take my own query. Let's believe that it exists already, right? I take this component here that I have now magically times my own key, right? Intuitively, the query is sort of who am I now currently, right? You'll see in the next one, this is maybe helpful. I'm still representing the. I take the query from the, right? This is what do I want to represent myself, the. And this here is the what do I give, right? So also what do I send when I'm being used as context, right? This is my key. And you'll see that I'm going through these keys. So in representing the strength for how much brown should I load into the, I use this query here. This is where I come from. And I cast to the key. Oh, sorry, I should do this. I apologize to the remote folks. I should use this key here as how much information do I send, right? And this is just about the strength here. And I do this through, right? So I'm still representing the, and I want to know what contribution should dog give. Well, I calculate just the product of these two, right? And then finally, I do the same thing with this key here, right? So far, so good, right? So queries, who am I? What do I want to represent? Keys, what do I give when I am being used as context, right? So this gives me these nice numbers here. Now, we normalize this a bit to get our weights, right? So this, we divide this by the length. So if you have, for example, 64 long vectors here, then square root of that would be 8, right? So this is the length of these guys here, and the square root of that, we normalize by that, and put this again through a sigmoid so that they sum up to 1. All right. So now, what do I have? I have these weights here, strength of contribution for all these different words, and they sum up to 1, right? So the degree of attention I'm paying to all the other words, myself, not at all, and or no, myself a lot, right? And then 0.1 here, 1% here, nothing back here in representing the. And now comes the final step, which is these values, right? And these values represent what do I give, right, when I am being used as context. So what happens now is the strength that I've determined before, keys and values, keys and queries and keys, right? This leads to these A's here, to the strength of contribution. And this is not just my weight. And what I'm multiplying in is really the context I'm sending, right? What's the information I'm shipping if I'm being used as context in this strength of degree. So it's finally my Z here is really just a weighted sum, right? And I can do this. Okay, so this was a lot to unpack now. I see frowns and they're absolutely justified because one needs to see this a bunch of times. Any questions at this point? Yes.
Earlier on, you said the key, where what do I give when I'm being used in context, and then you said it again with A.
Oh, sorry, no. So the key and the query, these two we try to match with one another, right? So the product of these two is becomes eventually after some massaging becomes my A, right? So query and key, you can almost think of that as a database lookup or something like that. How much does the key thing match my query, right? So what's the strength of relationship between those two? And that eventually then becomes my A's here, right? So how much should I look there? And then times what am I really looking at, right? And this is interestingly not the same as the raw embedding of the word. Yes.
What kind of information during the key and the value might have in or out?
Yeah, so these are really just numeric vectors, right? So it's hard to say that, right? What explicitly is in these, but they will try to capture, of course, some of the meaning here of the sentence. You will very often see syntactic information in there, right? So you will see that, say you have a relative clause, right? So what was my other example? The cat did not cross the street, comma, it was too tired, right? So think of that sentence. Now, the it, for example, here, it refers to the cat in that sentence, right? It was not the street that was tired or something like that. So in this case, it will learn to attend a lot to cat, right? So it just normally, right, means nothing because it's a stop word, right? This is one of these words that we would throw out immediately. However, here it's syntactically, it's a placeholder for cat, right? Cat was tired. And that means that ideally I want my it to have more or less the same representation as cat in this example, right? And this is what we're trying to achieve with this, right? So we are trying to match the syntactic structure so that I can learn to relate these things with one another. Say again?
Context related.
Context related things.
Trying potential context related.
Well, so this is the how much the context should influence the meaning of, so if you think about your recruits being green, right? If I want to represent green, the presence of the word recruits says something, right? So this might indicate already, oh, there's this sort of military going on or some form of maybe experience going on, recruits are people in training, right? So that might indicate that we're actually not talking about the color, right? So you're loading some of the recruitness, right? Or of the traineeness of these learning soldiers into the color green, right, or into the word green. And similarly, if you see the word t-shirt being green, you say, oh, this is probably, now we're talking about the color, right? And policy and green, you know immediately, oh, this is environmentally friendly or aware stuff. So this is what you want to do here, right? And this is what you try and cover in this 3-step process. And it's interesting that you can basically, via this division into 3 here, you can cover or divide and conquer the strength of association from what it is that you're sending, right? So out of this very rich context, maybe that each individual word has, we now have the freedom to just send parts of that, right? So because I'm not sending my full X1 here, but I'm sending my V, right? My value that I'm giving as the context for the next person embedding me. Yes.
Is it the output from the,
I hope I have this here.
like, is it the X1 which got
Yeah.
to it?
Where I think
It's just a representation from X1?
yeah. So
The network?
yeah, no. So these are different. So for each of these components here, so for my queries, my keys, my values, I'm supposed to show here. Queries, keys, values, I have a dedicated weight matrix. So I have a thing that turns X's into queries, right? And I have a thing that turns X's into keys and X's into values. So I have basically 3 separate neural nets that learn how to transform my raw content here into a query, the thing I search with, into a key, the thing that I try to match to, and into these values, the thing I transmit. That part, however, is global, right? So this we learn once. So different occurrences of the, for example, if this is not already contextualized, might be the case, but if this is a static word embedding here at this point, the queries, keys, and values, thank you, are going to be the same, right? So that would mean that every the searches for, latches onto, and passes on the same type of information, right? Doesn't have to be the case because I can have multiple rounds of this, as we'll see in a moment. More complexity and more stacking is better. And then maybe these are contextualized already, and it's not going to be static at that point, right? But so these are being produced first, and then I move on from there.
So in order to compute all of this, we need to know how long the sentence is, right? Because we need to know how long
Yes.
different ways, like
So
keys and everything.
exactly. So especially at this stage, right? So you can compute all of this stuff here, irrespective of what's going on. Right. So these guys here, so your S's from your queries and keys, you can compute irrespective. But once you normalize and once you put everything through a joint sigmoid, right, or softmax, then this is where you want to make sure that you have your entire sentence, right? So or whatever your context is. And very, very often your context will just be a fixed length window. So you know that you can have whatever it is, 500 tokens or 700 tokens, and that's the end. Chunk in the next question there.
I was going to ask, what is still?
What is what here?
The previous slide.
That's a matrix, the W's here.
Yeah, exactly.
It's just a matrix of weights. Wait, what, sorry? Weight of what? This is just a matrix of numerical values. So it's learned, it's a learned neural network. Right, so in a multi-layer perceptron, right? So you have your raw input values times some weights plus some intercept, right? This is your f times x plus b. And it's the same thing again here, right? So these are really the values here, the matrix here that transforms these raw word embeddings into your queries, your keys, your values, right? It's really just a linear transformation, if you will. And all of these are learnable, right? So these matrices here, anything that you do upstream, right? All of these are the learnable parameters of your model. So we backpropagate into all of these, right? And this is why things like modern language models, next week is going to be, or in 2 weeks actually, is going to be a lot on those. Why they are such heavyweights, right? It's because we're dragging along a lot of these matrices. They are already not small, and there's many of them. Yes.
Can the value be thought of as like a more local representation of the embedding? So like, I don't know, we had the word vector,
Mhm.
and in general, it means this, but in our particular context of our model, should we interpret that like a...
Yeah, it's a bit, so we have to be really careful. I end up saying these things also, but we have to be really careful here with the vocabulary, right? So it's at this point, it's not contextualized, right? So it's a transformation that is, what is the meaning I'm sending whenever I'm being used as context, right? So query and key is strength of association. And this value here is really the nature of the information I'm sending when you use me as context, right? So if dog is being used as context, irrespective of where we are now with context, right? Where every time you use dog here as context, what is that sending? Right, and that's what lives in these V's here, and that's what basically this WV here learns to get out of the raw embeddings. Right? But it's a bit of a contrived machinery. Yes.
So I had a related question.
Mhm.
So first, I am thinking of the values as, so for example, I would assume the value of to have much lower weights than say the value of dog or the value of brown, because it says less about the context. Is that?
I think that's a fair assumption to make, yeah.
And then when you say, so this is what dog contributes when it's as context, which that would be the value.
Yeah.
Is that still not as decontextualized as the rest? It's just like, well, this is what dog, any dog, or green, any green, contributes to the context. So to me, it just seems like an extra step. You know? 'Cause
Yeah.
I don't really see where the context comes in within the value.
It does not.
It does not.
No, so this tries to transport the essence of, so the problem with, I think, all of these is these original X's here, right? They were trained in a certain way. So say these are raw word to vec, right? So association of similar words with similar words. Right, so this is not contextual at all. And all that this thing here tries to do is give me the essence that I tend to need for doing downstream tasks, right? Because we train this in some end-to-end pipeline. That I need to carry on from this word, right? So this is basically a way of saying, okay, I might not need all of the thing that was represented in the or in dog or whatever, and here's the essence, right? So here's the thing you need in order to understand this thing as context, right? But that's, unfortunately, it remains a bit hand-wavy like this because these are extremely large architectures, right? And it's not so clear what exactly lives in all of these. And so a lot of work right now, since we have self-attention and transformers, which sort of goes hand in hand, right? A lot of work goes into understanding and reverse engineering what's really living in these and what's captured in them and what isn't. Right. Okay. Good. So these are great questions. All right. In the slides here, and this is mostly for you guys when you want to look at them, there's another example in there that's completely worked also, right? So where we have where we're producing the embedding for the second word here. Let's look at it real quick. Follows exactly the same scheme, and then you can, if you're confused, you can look at it at home once more to see whether this really latched on, and otherwise we talk about it in the next week, right? But again, I'm now representing brown, right? So I want my Z here, my Z2 for brown. I'm starting out, this becomes my query for everything I do in this step. Q2 here, the query for brown, I'm searching for brown. I'm latching this on to the keys at the, at brown, at dog, at ran, right? So I'm going through like these, compute my S's here. This gives me, after some massaging, the strength of association for all of these when representing brown, right? And you see that brown here in this example latches on mostly to dog. Tiny bit to running, tiny bit to itself, but really brown here means more or less the same as dog, which is interesting. Brown dogs being different from, I don't know, brown soldiers or so in German history. Okay, and now we do the same thing again, right? So now what counts, now that I have these weights here, these A's, is only the values of these guys. So I'm taking A1 times V1, A2 times V2, and so on, and summing all of these up, and this gives me my Z, my new contextualized representation that I can use to capture the meaning of Brown in the context of the sentence "the brown dog ran." So in this together, so this entire machinery here together is what we call an attention head, right, or a self-attention head. And you'll have heard that vocabulary before, I think. So attention heads are all the rage right now and are powerful. Okay, brief little checkpoint. Why do these? The big strength here is they're context aware. They're much more powerful than static embeddings. They sort of harness a lot of what we've seen in attention, but already at the representation stage. And by teasing it apart into queries, keys, and values, I have an extremely sensitive machinery that allows me to perform a lot of very sophisticated operations. The problem in these is, first of all, much slower to train, right? Because I have a multiple of the complexity in here that I had before. Right? Previously, this was potentially all nothing, right? So previously, I might have just looked up in my database, well, what's the embedding for Brown? Okay, here I go, I compute with that. Now I do all of this out of nowhere, right? For a better representation, but it didn't yet generate me anything. Right? It's really just a better representation of the entity. And the big cost, right? We can't pre-compute. I can't anymore, like in 2013, store this and say, I just look up at the cost of whatever hash table lookup or so. But instead now, if I see a new sentence, I might have to, at inference time, run GPU, right? And that was new. So prior to these models, what we would usually do is train these models on large, expensive hardware, right? Lots of GPUs. I have the model then, and inference is fast. That was always the tenet of machine learning. Training is okay if it's slow. Inference needs to be lightning fast. Now suddenly inference has this step that is sort of like training a bit, right? So because it's so massively parallel again, that my inference becomes slow and I need expensive hardware then. Right? So Google search engine or all the others as well, right? Was always the idea, train the search engine model once expensively, and every single query, because I get billions and billions of those a day, right, needs to be really cheap and really fast. Now every query goes through a transformer model, which really wants to ideally eat a GPU, right? So that's terrible news for sort of running my data center. So this is not nothing, right? Because very often we say, yeah, okay, sure, it's a bit more expensive. So what? This might break your business model, right, if you're running a company.
What kind of operation do you run?
What kind of what? Sorry, I missed that word.
What kind of things? It's not like training is slow and predicting is fast. Here, predicting is not like as fast as the other.
It's first of all, it's slower, but the big deal here is you can't have a big lookup table, right? In word embedding land, in word2vec land, we were able to say, okay, for the 50,000 words of the English language, I make embeddings at home, right? And now whenever I use them, I just, at a complexity of 1, I just pull them out of some hash table that I keep in memory. Super easy. Here, I can't do this because every word is contextualized in the context that it appears in, right? So if you say a sentence, the only way I would have in order to pre-compute this is store all possible sentences of the English language. That takes a moment, so we don't do that. And this is exactly why we can't play that game anymore. So that means we have to compute maybe with some tricks, right? And there are some tricks to make this a bit less terribly slow, but you have to compute on the spot. Right? So this is what I mean. So all of these lookup tricks of, oh, let me just memorize the whole thing, don't work anymore.
Which is here to use here the static embeddings, right? Like, for instance,
Yeah, static is great. Lookup. Contextualized is great because richer, more descriptive, but expensive because I have to do it now. Right? It's not just expensive to get there, but it's expensive every time I use them, and that's a big deal. Okay, and this gets us to transformers, which is the last block of the day. We have plenty of time for this because you guys are great. keep the questions coming if there are any, right? But the heavy part you've breathed through, this is good. Transformers are basically self-attention, right? So the paper that introduces these, if you haven't seen it yet, is called Attention is All You Need. So when we had attention for a year and a bit or so, or 2 years, everyone put attention into their flavored models, and this was all good then, this helped a bit. And then at some point, someone started just switching off everything else and just operating with the model minus the model, but more attention, right? And this is what we know as transformers. I mean, this is sort of mean. There's definitely contributions in there, but really, by and large, it's just massive reliance on self-attention, and we'll see that in a moment. Okay. So we have our contextualized embeddings here, right? So our Z's, that's what we just developed via our attention head. What we can do now in order to make these things even richer and again cover more semantics is to have some feed-forward layers again in there, right? So this eventually is of course the case when we're producing things, but it might already help us transform these embeddings here as we go through the next step, right? And we're further going to play a few tricks. I'll start at the back here. Layer normalization really just tries to keep the values of the components in here within range. So this, all that this means is I take this guy, let's say whatever comes out here, right? So I run this through another feed-forward neural net, and the gradients that I'm passing back here in training this, I'm really just taking these and I'm renormalizing, right, at that stage. So I'm really just saying what's the mean and the standard deviation, fit that to zero mean and unit variance, and pass that on just to keep numerical stability here. So super easy step. And then the other thing that I'm building in are residual connections. And you may have seen these in computer vision models. All this means is I take the thing from before, this guy here, and I also lead it into the after, right? So I have a way of still looking at what happened before the last processing step and get some of the raw information in there, right? And the great thing about this is I can compute all of these in parallel, right? So I hope you guys see that. Previously, I had this nasty little arrow here in between, right? So my RNNs and my LSTMs, right? They always wanted to have me pass on information. I can compute this guy here, but only once I've computed that guy. That's really terrible for parallelism, right? Because that means I have to wait here. This guy here has to wait quite a while until this information trickles down. Now, what we can do here doesn't have any of that anymore, right? So I can compute this guy and this guy and this guy, all of them in parallel if I have parallel compute, right? This is why we like GPUs again for this, and can just slot that whole thing up. And of course, at this stage here, this feed-forward layer has to wait for all of them, but a lot of this contextualization I can do in parallel, right? Which is great and very powerful. Okay, and I think I have a good figure for this later. But so this might be what our encoder looks like. So remember, encoder was represent information that was given to me. Decoder was do something with that such that we in the end solve our task well, right? But this is usually what you'll see in your models here. Right? And now we had this question of positionality, right? So right now, if you look at all of these here, this is location invariant, right? So whether brown was the first or the second or the third word doesn't matter, right? You will always get given the same context, right? Whether I say the brown dog ran or the dog brown ran, makes no difference whatsoever. Gives you exactly the same representation in the end, right? Does everyone see that? Support. Here, it might not matter, right? Because this is sort of silly. If the dog chases the cat or the cat chases the dog, that means something, right? That matters, right? Also in our internal model of what does that crazy cat look like then. So we might want to actively encode here where in the sentence a certain word occurs. Yes?
Good question. So say we run this model on parallel, right? So how about the context-dependent stuff, for instance, the precedence and the upcoming stuff? So how can we catch them, or how can we solve this in terms of parallel computing?
Mm-hmm. Yeah. So, but so I think so. The parallelization here is not affected by sentence order, right? By preceding or succeeding information, right? So this really just says, I can compute this thing here using all the others, but independent of order, right? So all I need is the entire sentence. And if I have the entire sentence, there's no sequential processing, right? So everything can happen in parallel here, because all I need to say is, give me your quiz queries. Quiz are going to be a word at some point. Queries, keys, and values. And if you give me those, I can compute everything I need. Right? There's nothing that I need that needs to have waited for the first 3 words or something like that. Right? Does that make sense?
Yeah, for instance, like, I don't know, like adjective before something that makes sense. So there is always dependency in the language, right? So how can we transform or apply this kind of dependency in terms of parallelization here?
Yeah, so the dependency you get in, right? Because now, so what you have here is now say you magically got your improved representations, your Z's here, right? You will, in the next step, then convolve them with one another, right? So now you here have some feed-forward neural network that cooks something out of all of them, let's say. Right?
The further steps we're going to.
Yeah, but so in the next step, so once the next attention head comes, and we'll see in a moment, right? We're stacking these again because we like to stack things. That's then when we can cook these things up from one another. And I can, of course, already here in the representation say, okay, because I understand sentence structure, I can already know that it means cat in that other example I gave, right? So I can already load that into these representations here. That's not a problem. All I mean here is I have that if I'm allowed to translate, let's say, right? So if we're talking machine translation, I have all information available at the same time. And that means I can do it in parallel. If you machine translate via an LSTM or RNN, you can't, because you have to play this game, right, where you go through all the steps. And this is just from the architecture here, a huge advantage, because if we have things like GPUs or TPUs or whatnot, architectures that do massively parallel multiplications, which is everything we do, right? We only ever multiply and add a few things, right? That is great, because that means like I can look at how large my context is and do that in one step. And I do this basically at no increased cost in time. It's increased cost in electricity, of course. But other than that, it's the same. Does that? Yeah. Okay.
But also the memory goes up. Right?
Oh yeah, sure. But so very often with these, we care about cost and time, right? So if I hit max hardware, how far in sequential land do I have to go in order to solve my task? Right, so you will always sort of max out your memory or your whatever, right? And then at that point, you have to do things more slowly, and that's sort of the equation you're seeing play out here, right? So fill up your thing, right? So if everyone has enough memory to run 700 whatnot tokens, right, or 1,000 tokens nowadays, maybe, then that's your context window, right, times the size of each of these words, and that is then what you're operating with, right? So we are wasteful in terms of memory, and wasteful definitely in terms of electricity, but what we are concerned about is time, because that's what we perceive as the scarce resource. And I mean, that's up to everyone else to see whether that's wise for our living longer on this little ball in space here, but that's the way we construct these.
So we speak of context window size in LLMs. That's sort of what they mean.
That's exactly what they mean. So that's how many of these guys here next to one another, right? That's your context window. Sort of. We'll see that in a moment, right? But let's believe that's the number of words here, right? It's actually tokens, right? So some of these words here, these raw words might become multiple tokens, but that's your context window. Yeah. Okay. So now what we do here, so remember again, the idea was positionality. It matters whether the dog chases the cat or the other way around. What we do here is add positional information, right? So and there's this nice little, if you're into all of that. So if you have your sine and your cosine and you multiply those together, you get a super nice positional encoding that sort of never reoccurs, right? So you have something that's sort of like enumerating your sentence and saying, well, you're in the first position and you're in the fifth position and so on, which gives you really nice benefits here. Truly, all that happens is that you put the positional embedding, and we'll have a figure of that down here already, right? So you would say, in my representation, So before I even do queries, keys, and values and all that good stuff, I'm saying, here comes a the, which is happening at position 1, and here comes a dog, which is happening at position 3. Right? And that now helps you in a sort of mathematically sensible way to keep track of where in the sentence we are. And this also allows us to later on play things like autoregression, right? So I might give you the whole thing, but I'm masking some of the positions out so that I tell you can't look farther than some position that I'm allowing you to look at, right? So this is a pretty pivotal component of all these modern architectures. Okay. And now comes the computer scientist again, right? So now all the exciting stuff has happened, and we let the engineers in, right? And that always means that stuff is getting nasty. So we could now try and understand the world better and have a more sophisticated model, or we just make it bigger. Bigger is great because, again, that saves my time, right? So I don't have to think with this thing anymore, and I instead just add complexity onto the model, and the model does more. Okay, so if my queries, not my queries, my keys and my values can relate to one another in a certain way, that's maybe not the only one, right? So that's why I might want to have multiple of these computations, so multiple of these matrices here at every step. So my attention head might actually become an attention hydra with multiple heads, right? Think of convolutional neural networks if you've seen these, right? I have many filters at the same time because I'm looking for different aspects in that pixel or concept space, right? And I'm doing exactly the same thing here. So I'm using many of these guys, so I'm not producing one Z for the word one, but maybe 3, right? Or maybe 8 at every time. So you're already seeing that this guy here now becomes some form of tensor again. This means that the matrices that I need for this here become a bit bigger, right? So everything becomes nasty and big in parallel. But now I have the ability to capture different parts of the relationship, so different contextualizations of the at the same time. So I'm using multiple copies of these. Okay. So quick recap, and then we're also almost at the end of it with plenty of time for questions and discussion. The whole goal of all of this, right, was to get at the best representation. So again, we haven't made any predictions here. Nothing in the transformer architecture actually does better inference. Right? The inference at the very end is really a bunch of stacked feed-forward layers. This is stuff that we knew in the 80s. All that we changed, all that's different is just the representation, right? And I'm saying just, but it's a lot, right? So all the complexity goes into this. 99% of the compute goes into that. Once you're done with the representation, inference is super easy because you now have such a rich representation of the thing in the real world, of the text, of the image, right? That inference basically happens on its own because hopefully you have some form of subspace that already divides this thing by task. Here's another, that's my question. Here's another way of visualizing these things, right? So if we zoom out a tiny bit again, back to sort of what I showed you in the beginning, you'll very often see these forms of diagrams, right? So you have your input, you embed that in some way, you put this positional encoding here, this sine and cosine game in there, right? So you just add these up, right? So here's my word the represented in maybe word2vec space plus positional encoding. This goes into 8 usually attention heads at the same time. After that, I normalize, I add again the raw stuff, right? So this is my residual connection. I have my feed forward layer, I again add and normalize, right? So again, have a bit of engineering here. And this is now really one multi-headed attention decoder. So there's a lot going on in these, right? Because these matrices, these Ws that produce these guys here are not small. And now I have 24 of them at the very least, right? So there's lots of parallelism. And oops. And this is sort of what gives me my encoder. But the game is not over yet, because again, engineers entering the stage, right? And I can stack these on top of one another, right? So I can have multiple layers of playing this game, right? And I can say, okay, there's maybe another 8 of those stacked, or maybe it's 3, right? Depending on whatever we want to do. That again, eat what came out of the previous layers and sort of again newly contextualize this and pass this on until at some point I have my final representation. And this is when I'm basically done, right? This is when basically nothing happens anymore. But if you imagine that you have to, in order to train these guys here, you have to back propagate, which was costly because of partial derivatives, right? So nasty math into everything here. This is why we are looking at whatever it was, 1.7 trillion parameters or something in modern models, right? So this takes a whole moment, yeah.
So if we train on the big text, or like a lot of text, every word is connected with every other word through this contextual.
Within the context window.
Yeah.
But yes, right. So of course you have, at some point you reach the length of the context and then that cuts basically. But you see a lot of texts, right? So you will see not just dogs, but also cats and maybe birds and other things chase other things, right? So, and this is why you will have a lot of contextualization over time. We throw most of this away, right? So the concrete contextualization of Brown here, say we're training right now, we read the sentence, we never memorize, oh, I just contextualize Brown in a certain way, right? This all goes away because I'll recompute this again on the fly. But where this goes is it feeds into all these W, V, Q, and Ks, right? So I learn how to better contextualize via keys, queries, and values. But that's the only thing I keep. The concrete embeddings of here's the super contextualized Brown when using in this sentence here, right? It's completely gone. Okay. Now, we talked a lot about encoders. Here's a decoder, right? A lot of these models came from the machine translation world, where the goal is always sequence in, sequence out, right? Seek to seek, sequence to sequence processing. The decoders, luckily for us, look pretty much like our encoders. All they have in addition here is another attention head, right? And we'll see in a moment what this thing is for. This basically takes in the output from the encoders, right? So I'm having the output, right, again, shifted in this teacher forcing or otherwise way, right, where I'm starting at the sentence start and I'm generating the first word. Based on the first word, I'm generating the second word, right? So this is what I have generated already, also with conditional, with positional encodings. And then I'm using my self-attention here. I have my encoder attention, right? So how much attention do I need to pay to the things that were encoded already? And how much attention do I pay to the things I'm writing? And then I have my feed forward plus a bit of engineering here in yellow. So this is what this looks like high level. So I'm stacking up my encoders. Usually it's 8 right now. And then this final encoder here, so my best guess at how to represent this information, goes into all of the decoders at every time I have access to this guy here. Right? And then I'm producing through. So every one of these guys here can look at what was decoded already and what was encoded. Right? So pretty much the same thing. Does this make sense? Right, so this is a lot of heavy lifting. And this is also, you see now, this is the reason why we need pretty sophisticated introspection methods if we want to understand what these models do, right? Because it's pretty heavyweight what's going on under the hood. And there's no way that any human being, even the smarter ones among us, could understand what's going on in these models otherwise, right? If you just go in and say, oh, look, this is what this vector, 760 dimensions long, what this looks like, or whatever, right? So just numbers. So really, this is why a lot of sophistication has gone into the transparency here. Okay. Good. So this is what this looks like in a bit more detail, right? Again, this is all the stuff we talked about earlier. We have our encoder blocks, we have our decoder blocks. So these are really just different. I'm just throwing different diagrams at you that sort of capture the same stuff, but in different levels of resolution, which sometimes helps, right? So this has maybe a bit more detail, but it's really everything that we had before, right? And this now hopefully gives us, oh, it's even with a nice animation where our information goes through and then becomes queries and values. I kid you not, man, it's hard. And I start generating these outputs here. as I'm going through the steps. Okay. So, and these are our little encoders and decoders. Now, what does this do for us if we have this, right? So this is what basically everything runs on right now. So we have a few language model architectures like Mamba that maybe are a bit different. But does this help us at all, right? Why is this so dominant? It comes at greater cost, right? So we'll see that self-attention in itself is quadratic in my context, right? So the more words or tokens I consider to take in, the rapidly more complex this will get. And I didn't have that in recurrent neural nets or maybe in convolutional ones, right? There are some tricks that we can play, but they only get us so far, right? So I can get the quadratic nature out of here, but at the cost of sort of more complexity of these components becoming bigger. Okay. Now, what does this tell us? These models are pretty good at a lot of things they do, right? So this is a machine translation task from English to German or from English to French. And we see that at massively increased cost, right? So we are going potentially, oh, it's actually not so bad, this one. Okay. We get to pretty solid numbers again. Interesting are properties like these, right? So the concrete numbers, okay. But this was an interesting scheme, right? Where when these transformers were new, there was a nice paper that showed that if you learn to translate from language A to B and then from B to C in a new model, right? Or in the same model, sorry, you actually get a pretty decent translation from A to C, right? Because we are via all these interactions, via this complexity, again, I'm incurring beatings from Michael, we're getting closer to word meaning, right? To semantics. Right, and if we have a good understanding of semantics here and semantics here, then this should hopefully allow us to map this as well from A to C directly. All right, so final thing for today, and then you survive this somewhat dense class with lots of content, is going to be BERT. And lots of you will have heard about BERT as one of these concrete architectures. It's Elmo's friend, right, both in Sesame Street as well as here. So motivated by the fact that all good models need to have a Sesame Street reference, BERT has one too. And here the idea is, what if we don't want to decode, translate, produce language, right? So all we want is a good representation, just an encoder. And we then want to use that for our downstream tasks. So along comes this guy, so the bidirectional encoder representations from transformers. Right? And you already see that we're playing this whole bidirectionality game again, because apparently that's still on the table here. And we'll see how that works. So we're doing bidirectionality, only encoders, virtual representations. Okay. Architecture-wise, exactly what you've seen before, right? No news here. If you've understood attention heads, right, this is exactly what's happening. The main contribution here of BERT were two interesting training objectives in which they were pre-training this on language, right? The first one is masked language modeling. So this means that at training, once in a while, I'm withholding a word here, and I'm trying to predict the missing word, right? So I'm trying to fill in the gaps that I stochastically create in here. And this works roughly like this. 15% of your words are masked in some way, right? 80% of those become a special token where you usually just say, this is black, right? This is masked out. You have to guess what word this was. 10%, I put the original word in, right? Because I want the ability to predict the word itself from the word, right? So I want that kind of flexibility. And for 10% of these 15, right? So that I masked here, I put a wrong word in, right? So I want robustness to noise. So I want you to predict from context the correct word, even if I give you something that's not a mask token and that's not the correct token, right? I want, again, robustness baked into this model. And this is interesting. So this is sort of metaphorically, very often the way to get your model to be better is to make the task harder, right? So very often the game is, oh, if you're pretty good at this, what with one arm on your back, right? What without arms? Or actually you also get blindfolded during, and so on. And if you're able to do this under harder conditions, and BERT really is a typical example of, oh, let's make this game really hard. then probably you're forced to understand the problem better, right? Because you now have to pay attention to the nuances or to the parts of the problem that I'm still giving you in order to get better at this. So you'll see this for lots of machine learning problems. If you make the task harder, given that your model learns something already, right? If you make it abominably hard, and then you might not learn anything. That helps you perform this. So this is the first task here, masked language modeling, right? I take the original sentence, I mask out words, I juggle around with these masks a bit, and I try to repredict the original sentence from it. This is great news because it's self-supervised, right? So there's no manual annotation whatsoever. So none of the whole GPT craze could have happened had we had a need for manual annotation in there, right? So later on, bit of human feedback and whatnot, reinforcement learning, we'll do this in a few weeks. But at this early stage, really everything that happens here is completely driven by, I have lots of unsupervised text, right? And I just try to recreate noise down versions of the text. And then the second objective in here is I'm feeding in 2 sentences at the same time. And you have to tell me whether the second sentence was actually the sentence that followed on the first. Right. So I'll give you half of the time the actual subsequent sentence, and half of the time you get something that's just some random sentence, right? And this again helps you beyond sentence boundary to look at, does this flow, right? Is this actually natural text or is it not at a longer range than what you locally get maybe with your masked models? And this together gave us a pretty strong representation without any real engineering advantages, I guess, right? So this or any sort of model advances. So this was really just lots of engineering in order to train this model to the best of its ability, right? Okay. In practice, what we're doing here is we use this on not raw words, but we are even using subword units, right? So if you're thinking about syllables like the, d or re or whatever, right? This will already tell you something about the function of the word in some ways, right? So if you learn about all these prefixes or suffixes, you can actually model semantics on that pretty well. So this is why we tokenize, we learn to tokenize. So we're not doing any of this split on white space character, but instead we have another supervised trained model that tokenizes, and then that goes into these models, right? And now the last question that we have here is, since these are just encoders, how do we represent, right? Because we wanted a representation out of this, and what do we do here? And usually what you would use is either the final layer or some form of average of the last hidden layer. So what people have found is that sort of a concatenation of the last 4 hidden layers is something that performs pretty well on a bunch of tasks here, right? So this shows you that early layers tend to have less meaning. They have gone through fewer of all of these contextualization exercises, are less informative than high layers. Yes.
There's this score, you know, much better in ChatGPT.
In these scores?
Yeah.
I mean,
much better because like there isn't much.
Yeah.
It's 100 right at the top.
Yeah, there's not much headroom here. So this really depends on the task and the data set you're looking at, right? So there's tasks in which we can't get better anymore because that tiny bit of performance that we don't get, this is even where humans wouldn't quite get, right? Because the ground truth might be arguable. So 3 humans might come up with very different ways of solving this. The label might be altogether wrong if you have a label there, right? So this is what we often see. The usual answer, I mean, so ChatGPT in a lot of these will not be much better, right? So you might tickle another, and this is what I meant with these diminishing returns, right? So you might tickle another percentage point out of here, which is huge because nobody else can, but it's not twice as good because it can't be. The game we play then is make the task harder, right? So what if we are generative in task, or if this is a task that other models can't solve, and then you hopefully see better improvements, right? And especially with generative, which BERT here, for example, can't do, there we see a lot of additional capacities of these models. Okay. So still for a lot of tasks, BERT seems to be the state of the art, right? So you can, of course, have larger or smaller versions of it. But compared with a lot of other architectures, if you are after classification or regression, a BERT-based model is a very decent baseline. It's nice because you can get this pre-trained. You fine-tune it a bit for the task you have at hand, right? So if you get something that's pre-trained and you fine-tune this thing for making diagnoses or whatnot, right? You have a pretty powerful model at relatively affordably, let's say, right, at this point. Yes?
Why?
Because it's only encoders at this point, right? So we cut away the part that says now decode and generate language with this. There's another interesting paper that's called Bird Has a Mouth and It Wants to Speak, where people try to get transparency into these bird representations. The play of that paper is beware your training data might be memorized in these models, right? So you might be able to get, if you were to do this on patient data in a hospital setting, right, you might be able to, and you throw away the patient data after and give the model to the world, they might still be able to read out that Carsten has some whatever worries about his reproductive health or whatnot, right? So there might be confidential information in there that you don't want the world to see, right? But in order to do that, they had to sort of build some functionality in there where you are allowed to sort of read out the attention heads. And if I were to ask you, the last attention head of the encoder, to generate something now, what would you say, right? That's sort of the game here. But this model in itself is really only meant for building powerful representations, not for generating anything, right? Just because we cut the decoders away. All right. So in summary, where are we at with this? BERT and friends, right? So transformer-based models, great for embedding learning, really powerful for transfer learning, and no direct generative capacities in this particular model, right? Many other architectures have these generators in there. All right. And this is the end of the day. You survived. Congratulations. And we did so in not even the full time. So this is great. I win my bet that nobody else knew I was having with them. So what did we see today? We had a real quick recap on RNNs and why they are tricky, right? So again, this V arrow over time is both its power, but also its curse in some ways, right? Because this gives us a very contrived, very indirect way of passing on information. We tried to make that more explicit by having LSTMs with their explicit forgetting and remembering, which works to some degree, but attention is more powerful, right? Because this, again, gives me at every point a view on my context. And in particular, self-attention, so contextualizing in my neighbors when I want to represent myself and doing this on steroids has been shown to be really powerful and is being used massively right now. Okay. So what's ahead of us? We have tutorials Friday and next week, but no lecture next week, right? So next Tuesday, there's not going to be a class. And then in 2 weeks, May 14th, Michael is going to be with you guys. And we're looking into large language models, in-context learning, and prompt voodoo. All right, so how to get these models to do better by asking really nicely. And then also in that week, your first big homework is going to be due. So I hope you have lots of fun working on those. Thank you so much.